I'm happy to welcome you all today, and the main speakers come from Amberg, both in Norway and Switzerland, maybe other places also. Most of you know me and the BA-Nettverket, and I will not, I'm Inger Hogstad, leading the BA-Nettverket in Norway, and I'm happy to announce Amberg today. So just present yourself, and you know who will present when. So
Tusen takk.
Ja.
Tusen takk, Inge. Jeg tar det på norsk i begynnelse, og de tar det over på engelsk etterpå. Så tusen takk, Inge, at vi får mulighet til å presentere våre tjenester og løsninger i regi av BA-Nettverket, og velkommen til alle. Jeg Biedermann, daglig leder her i Norge for Amberg Norge. Vi er et konsulentselskap som tilbyr tjenester i alle faser av underjordsprosjekter til både byggherre, entreprenører og konsulenter. Vi har bred og lang erfaring fra prosjektering både inn- og utlands, og besitter unike kunnskaper om kompliserte grunnforhold og ulike drivemetoder. Amberg Norge representerer Amberg-gruppen siden 10 år i Norge, og gruppen består av 4 hovedavdelinger. Amberg Engineering, som leverer prosjektering for underjordiske strukturer som jernbane, vei, T-bane, vannkraftanlegg og fjellrom, for eksempel. Det gjør vi med å arbeide modellbasert, i tillegg til å bruke innovative arbeidsmetoder som 4D, 5D og automatisert BIM-modellering. Den andre her Amberg Logley. De kombinerer moderne analyser og programvarer for smarte løsninger innen logistikk på byggeplassen. Amberg Technology en av de ledende leverandører av avanserte systemer og løsninger for å samle inn og forvalte informasjon om infrastruktur. Og den siste her, VSH Hagebach testanlegg, vårt fullskala 5 kilometer underjordisk tunnelanlegg med laboratorier, områder til produkttesting og trening i spesielle arbeidsmetoder. Der finner dere også et egen restaurant og lokaler for forskjellige arrangement. Den i Sveits. Tema for disse nettverkstreffene med BA-Nettverket ligger hos Amberg Technology, og vi har valgt ut 3 hovedtema. Amberg Rail, som dekker alle måleoppgaver som sporrelatert. Om dette får vi høre mer om en ukes tid. Amberg Tunnel, som dekker alle måleoppgaver som tunnelrelatert. For eksempel har de interessante løsninger for å spare også på antall stikkere som trenges på byggeplassen. Vi får mer informasjon om dette på nettverkstreffet 20. april på Fornebu. Og siste tema, som dagens tema, geofysikk med tunnelen Seismic Prediction, som Dickmann skal presentere oss nå. The floor is yours.
The floor is mine. That was the key word. I heard my name. Thank you, Joel. Thank you, everyone, for joining us to this lunch presentation. I already saw some very nice dishes on the tables there. I would like to join you, but my job today is here to present. So I will soon share my slide with you. I'm just checking my sound, if I include my computer sound. Yeah, that's somehow just checking. Now it should work. Good. The topic today is tunnel seismic prediction. You may have heard about this. My name is Dickmann. I'm heading the geophysics department of Amberg Technologies. We are located here in Regensdorf, close to Zurich, and we are working worldwide. So as part of the Amberg Technologies businesses, we have a geophysics department here, and we are dealing mainly with this very specific tunnel seismic prediction. Today we go into some technical details as well, but I will also explain you what is the purpose of that, and what are the results we can achieve with this. And later on, I hope you have also questions, so we can go on then with Q&A after my presentation. Good. As you know, we have usually, when we're talking about seismic, I mean, you are from Norway, you know a lot about geophysical work from the oil industry, which do seismics, of course, a lot for the exploration. And this is usually done in this way from the surface. As you see here, we have reflection seismic, we have refraction seismics, which is also sometimes used for the exploring the tunnel cores. And we have also cross-hole tomography using specific wells or boreholes vertically, or in specific cases also horizontally, where you have on the one side sources in a borehole, and on the other side receivers, and you are analyzing the wave path through the subsurface here. All this is, of course, as we know, kind of limited in forecasting the geology when it comes to tunneling. We have with tunneling we might have strongly changing ground conditions. We might have a high overburden, and using any kind of method from the surface is having, of course, limited depth penetration. When it comes to urban areas above tunnel route, then it's also limited to apply methods from the surface. And all this, of course, will also result in probably insufficient resolution, as we are quite far away from the target. That's why we come up with tunnel seismic prediction, as the name already tells us. We do it right out of the tunnel. You see in that sketch here that we have a couple of sources, and we deploy receivers directly into the sidewall of a tunnel. And we measure by sending out seismic waves from those source points here. We measure and analyze compression and shear waves. And so we pick up the signals coming back from any kind of reflection, from any kind of discontinuity in the area ahead, or even in the area around your tunnel. With this, of course, as you see, we are much closer to the target, so to the object we want to detect, whether it is a fault zone, whether it is a formation change, a cast hole, a cavity, whatever is changing in the geology, gives us and creates a good contrast in generating a good reflection back to our receivers. We also can then derive geotechnical parameters with this. I show you later how we do this by analyzing the velocities. So we are in the tunnel, and you see a typical layout here where we have a set of usually 24 little boreholes along the sidewall, right or left. And in a normal way, we have little explosive charges in the borehole, which will be ignited one after each other. And then for the back, we have 4 receivers, 2 left to right, where we pick up the signals. The whole procedure here in a standard survey takes about 15 to 90 minutes in the tunnel. So that is actually the downtime during which you should not do any kind of noise creating work. We will achieve about 150 meters prediction range or even more ahead of the phase, and get these results right on site if possible, or if necessary after about 3 to 4 hours. Accuracy is about 85 to 90% of detecting the targets there. according to our high signal resolution and according to our experience, of course. The experience is quite long. You see the TSP story, I would call it, started already in 1994 when we created the first, the so-called pioneer of the TSP system at Amberg Technologies. And then we had a long development route, and it's still going on because we are still developing everything further. And the most recent developments I like to focus on here and also like to present to you today is first the launch about a year ago of the new TSP 603 wireless system. And secondly, what we recently launched in last autumn, the TSP Impact, which is an impact hammer, a mechanical hammer, which is actually replacing the little explosive charges along the sidewall. The new TSP 603 wireless system, as you can see here, consists of course, receivers, but also little transceiver boxes. You see the antennas already here and a trigger box, which are working wirelessly. So they have independent power supply inside, and they send everything they should send, whatever the signal is, without any cables being connected to it. You will see that later. It works, of course, as it always works with TSP in drill and blast headings, but also in TBM heading. You see here a good picture from inside a double shield TBM using precast segment lining. And in this example here, we have used the grout holes in the center of the segments to install our receivers and to hook on here then the little transceivers being connected to the receivers and sending out the signals which it picks up and digitize from the receiver and send it then to a tablet, which the operator just has in his hand, just having this tablet PC and receiving and controlling everything from this. We'll come to this later. You see another picture how the transceiver is hooked up to the receiver in this kind of grout hole here. It's very lightweight and it works completely autonomous and has a quite long battery life, so it holds without charging for if it would go in a permanent operation of many days. The receiver is very lightweight. The whole system is only 2.7 kilograms. It consists of a receiver rod where at the end is the sensor included. It's a triaxial accelerometer picking up the seismic signals in a very high frequency range up to 5 kilohertz. And we have a protection tube here, which is actually protecting the receiver rod by, let's say, collapsing or from collapsing of the borehole, which may happen, so that in any case, the quite expensive sensors will be rescued in such a case. We have a dowel, which is consumable, and we have a specific size bond mortar, which is actually giving us the force coupling of the dowel to the rock mass, and both, so the dowel and the size bond is consumable. We have inside, which is also new, inside the sensor head here, we have also placed beside the accelerometer another sensor, which is an electronic compass and tilt meter, which is giving us the full orientation or alignment of our accelerometer inside the borehole. So meaning whatever the orientation of your borehole is, we will capture it and read it out directly into our software and can do later on a compensation on this. Transceiver, the trigger box works as well wirelessly. So whenever we get a trigger signal from the blast or from an impact of a hammer source, we will send it to all the devices within microseconds. So we are working with a very high accuracy of microseconds, also in the synchronization of all the devices, which is of course very important here. So this is a setup of the whole system. It's quite mobile, lightweight, and you can carry it into the tunnel for a measurement, take it back and go also into another heading. So it's not a fixed, let's say, installation in a tunnel as long as we look at this TSP 603 system over here. Yeah, this is a little movie. I hope you can also catch up the sound. I was trying to bring it over to you. So we are waiting for a shot along the sidewall.
Ready for shot?
There is a little shot hole here.
3, 2, 1, fire!
So there's a water fontaine actually getting out of the hole, which we use for tamping. And you have seen here on the sidewall, these blinking transceivers, they were actually waiting for the shot. And the operator here is just holding the tablet. And this tablet is also wireless, using wireless connection. And it's getting right after the shot, as you have seen here. So that was a real time, the seismic signals on the tablet, just having this in your hand. You see a little box over here. This is our own router. So we build up our own Wi-Fi network in the tunnel with this little box here. It's also autonomous. It's having its own battery supply in there, and it works really fantastic. It's creating our network completely independent of any other network inside the tunnel. Okay, now when we, as I said, when we like to replace or find an alternative for the explosives inside the tunnel, we know that explosives, in cases of using a TBM for tunneling, could be annoying. And people were asking, how can we replace this? We come up now, since last autumn, with TSP Impact. TSP Impact is actually an impact hammer, as you see from that sketch here, which is of some 65 centimeters long and 30 by 30 high and wide. It's quite small. It's weighing about 56 kilograms. You can separate it very easily by some screws in two parts, so that a person can also transport it and carry it to the location to mount to. And that works pneumatically. So what you need is a compressed air line of minimum 7 bar, which you usually have, for example, in a TBM available, but which you can also create from a little compressor, independent compressor, when you want to use it also at, let's say, alternative vehicles not within a TBM. This hammer can strike about 10 times in a minute, so very rapidly, and it's very powerful. You see, that is a usual, let's say, layout. You have this 2 pairs of receivers inside the wall, and you have now the new impact source, which you move along the side wall. And you have a compressed air compressor over here, our router, and a control unit to control the hammer, and your tablet, of course, which is having the communication with everything. You can install the hammer, for example, also at a drill jumbo, so at your drill rig, in order to use it at the face itself, not along the sidewall, but at the face. And with every blast, with every new blast round, you can use the hammer beforehand, have some minutes striking it, or just 1 or 2 or 3 minutes striking at the face, and create this controlled seismic signals over here. Or you use it along the sidewall in the standard way, as we usually do, mount it at a vehicle, which can be any kind of little vehicle in the tunnel available, which can be, for example, a mini excavator or something else. And you move then the vehicle along the side wall and create this waves. You see here a very nice and very fresh picture from which we have taken from a demonstration we have done in January in Japan. This is Shinkansen, a new Shinkansen line with 14-meter widths, so a very big profile. And we used here, installed the hammer at the tip of the arm of this little excavator. You see in front here the tablet having the full control of this hammer. So it's indicating now hammer is coupled to the wall, because the hammer couples itself towards the wall. And once it is coupled, it will then accelerate a mass inside the cylinder towards the wall to create the seismic waves. You see this here in this broadest way, that we have this little excavator moving along the side wall every 1 to 1.5 meters, make a stop for 2-3 minutes, and then strike and go on to the next position, while the little transceivers here along the side wall are picking up the waves. That's another movie. You see the hammer in operation. So there is nothing moving outside. It's totally safe. And here it is with a kind of 9 to 10 seconds interval strike. We do this some 5, 6, 7 times on the same spot in order to create here traces, seismic traces, which we later on stack on each other as a vertical stack, which generates a higher signal to noise ratio. Good, you see how it works here. So now when we're leaving drill and blast and we go into a TBM, where people also like to use the hammer here, you could have a scenario which is shown here. So we are now we go into, for example, a double shield TBM, and we know from a double shield TBM that usually everything is closed at the shield site, and then right after the shield we have the precast segment lining. So we are more or less going blindly into the rock mass. Scenario here is very similar. So we have through the grout holes, as you have seen before, our receivers 1.5 meter deep into the work mass, and then we try to find then an opening in the shield to let the hammer move through the opening and be force coupled to the side wall. That can happen by, I'll explain later. So then we have this source point over here creating these waves into the ground, and we are picking up those wavefronts which come from ahead or from the side to our receivers. So in a TBM, double sheet TBM scenario, you have this sketch here, and we look to the side, and we can have a telescopic front shield here, which can open here a little window in order to let the hammer, which is then being mounted on a console here, go through and be coupled to the side wall. Once the hammer then strikes towards the wall, we are picking up here at our receivers the signals. Everything works wirelessly, so that is the good thing here. Also with the 603 wireless system, we have no cables lying around here in this TBM environment. So the trigger signal actually is sent wirelessly to all the devices here, to the transceivers and to our tablet PC, and right away we see the data here on the tablet PC. This is how the hammer in a real case looks like, being screwed on, as you see here, on a metal console. This is a situation where we have the telescopic shield, which you can open here a bit, and you open it by some 25-30 centimeters so that the hammer can go through in the moment it should hammer. And that is usually the situation when you have done your stroke and then you have a standstill of the cutter head. So the machine has a standstill, and in this moment you can use the hammer. So machine is not moving, the wall is not moving, and we can stretch through the rock mass. The idea behind that is that we do, let's say, an exploration while excavating. So while you have with every stroke of your machine a little stop, which you actually have anyway, you use the hammer and you collect data, and you do this along while the machine is going ahead. Once you have collected enough data from enough shock points, we start doing the processing of the data and the evaluation. So, and that gives us then enough data to see ahead, even by using the hammer, which is, of course, in comparison to explosives, not that powerful. Here you see a comparison about seismic sources. We did it ourselves using, for example, explosives of some 50 grams. Let's have this as a signal amplitude of 100%. And we can compare it to the impact hammer, which is at least then at 30% of this. And compare also to a sledgehammer, 8 kilo sledgehammer, which you can use yourself hitting towards the wall, which also works with the system, which is giving you much less energy here. What is also good is that we can create with the hammer a signal frequency also in a wider range, up to kilohertz. And that is actually giving us then later on the resolution which we need. The prediction range ahead of the phase is also quite good. We know that we can achieve up to 100 meters with this ahead of the phase. So we are giving here ranges 80 to 120 meters, while of course with explosives, as they are more powerful, you can reach higher ranges here. Okay, this is hardware. Then it comes to software, which is also very essential. The Amberg TSP system consists also of a very powerful software package, which we call Amberg TSP. This is divided into two modules. One is for data acquisition, as you can see on the right-hand side, inside the tunnel, which is installed on the devices there. And the other part is the Amberg TSP processing module, which is someone using in the back office or on your construction site in the office there. And what you do then, right after data acquisition, you transfer the data to this module here, and the guy who is responsible for processing the data can do this right away. As you see, we have an Amberg cloud service. This is very new, and which is very, very comfortable. So people on site can just by some mouse clicks use the Amberg cloud transfer. This is free of charge. So they transfer the data into the Amberg cloud. They are being stored there. And the guy who is in charge of processing the data can do the same on his side. So he can download the data and he can start doing processing. That works in both directions, and it only works for this specific data set. So every customer will get a unique TSP ID on his data. So those data can't be processed or handled by other parties. So there's always a strict policy in this. So nobody else is entitled to get your data and to use your data. That is important. But what is also seen here, if you don't want to use the cloud service, you can, of course, easily use your pen drive and transfer the data from one PC to the other. Good. The software is quite nice software. It's used, or it's made and designed by us and created in order to have it available for, let's say, non-geophysicists as well. Like we have, let's say, geo people on site, like geologists, geotechnical engineers, and other professions. They will be trained by us, and they can easily apply the software after our training. So you have a straightforward user-guided project tree over here. You see raw data in the screen here of this 1 to, for example, 20 or 24 shot points, which you have collected. And then you go straight through this project tree and you are guided through the data processing. What you do also, you create your geometry model. So in this case, you see we can even import your land XML data, which comes from the design axis of your project. We can easily import it in and create your tunnel model over here, and use it then also for the analysis, of course, of the seismic data. So in a twin tube situation like we have here, in one tube we have used a survey, or we have done a survey over here with the spots of receivers and source points over here. Everything is nicely indicated and good to know in real and absolute coordinates. The processing of the data goes through a processing scheme of different filter processes, which are also guided by us, also when it comes to parameter settings. And finally, once you have done this 3D data processing as well, you get results like we call an evaluation set, where you have a tunnel phase situation here and a color shading, nice picture of different ground changes ahead of your face. And on top also characterized by different, accompanied by different parameters. I come to this later on. Here you see a zoom up of a situation from a real data set. We have the tunnel phase here, and we have this kind of transition zone from phyllite to gneiss, which is actually a broken zone, a kind of fracture zone in this red area here. And we can see that from our reflection data in the data, which we have analyzed, like the VP chart, so P wave velocity chart, the S wave velocity chart, and we derive out of this the Poisson's ratio and also a dynamical Young's modulus value along the tunnel axis. And so that gives us further characterization. Beside the reflection, which we analyze, we get also further information like this geotechnical parameters, which enable us to better characterize what is lying ahead. So not only there is something, but also what is it, in what way we have to keep, we have to be careful, and we have to evaluate this as kind of risky zone. When it comes to related to a comparison of geological findings, which is also very interesting for us and exciting, of course, because here we do geophysics in a way that we present a forecast, and we just have to wait till the forecasted stretch is being excavated, and we get a feedback from the site, from the geologist, of the geological observation, and we can right away also judge about the TSP results and the geological findings, and we can also then go into a kind of back analysis and fine-tune also the calibration of the velocities. So we can do like surface rendering of low velocity zones. As you can see here, this is a screenshot right of the 3D model we create in the software. And we can even do kind of build up a simplified geological model with planes and with transition zones for this example I have just shown. Other examples, as you can see here, surface rendered anomalies, so low velocity zones. For example, also here to the side, this red zone, which is actually a fault zone, going more or less sub-horizontally or sub-parallel to the tunnel axis. And you see there is the borehole indicated over here. We can put, this is a screenshot from the software, so we can put also the borehole information into our evaluation set, and we can also put information of the borehole from the geologist into here, and we can do a correlation between borehole parameters and the extracted zones from our seismic data. You see, there is the existing tunnel from where we have done the measurements, and there's another axis which we have also put into the model here. This blue arrow is a second axis of a tunnel which should be built later on. So this is a kind of investigation tunnel or exploratory tunnel for a main tunnel which will be excavated later. So you get right away also from the, let's say, pre-investigation from an exploratory gallery, you get information about your geology, which is important for planning and designing your main tunnel. Yeah, also here, if you look at it, it's a bit small. There's another borehole indicated here, which is indicating a damaged zone, which agrees to the surface rendered zone over here. So let's say the parameters, and out of this, the benefits which we can achieve from the TSP here is we analyze the PNS velocities ahead and around, which is giving us lithological parameters. We derive Young's modulus, but also the bulk modulus out of those velocity information, which is related to the stiffness of the rock mass. And by using the Poisson's ratio, which is directly derived from PNS wave information, we can even get an idea of water hazard zones. We cannot give you the amount of water in there, but we can indicate whether there is water or not in this bearing. Good. We have with all this, we have, of course, parameters then available, not only reflections, but also geotechnical parameters, which you can use to also to optimize your support. So when it comes to shotcreting or supporting how many anchors you need, so you can well prepare yourself in all the logistics on site when you know what kind of scenarios you should expect in front of the face. The TSP, what we understand is, let's say, a tool which prevents risk and failures which can happen in the tunnel and which happens in the tunnel all the time. And we can do this by an accuracy of 85 to 90%. This is according to our very long experience here. What we can also create out of the software is we can export the surface rendered data into kind of object format, which is quite useful to import the data then into a BIM system. So BIM is, of course, more and more important today on modern construction sites. So you can take the data from the TSP survey and put it into your BIM model. TSP is working around the world. You see, we are working in many countries, and the model is is quite easy because we actually in most cases do not services. We offer a system sale. So that's why the system is designed in a way that people can use it themselves on site. So this is our philosophy: bring the system to the site, train the people, and let the people on site do what they need to do. The benefits and operating efficiency of that is, when it comes to financial issues, is quite clear. Many people say, oh, the system is quite expensive, but they don't think about, let's say, a comparison to a downtime which is created by a geological failure. You see here, this is a very simple bar chart where you have a 1 kilometer up to 8 kilometer heading. And we calculated roughly in average what TSP costs are for such shorter or longer headings. And you see that for a 1 kilometer tunnel, we count about 3 days of time-dependent site cost you have on site, which costs the application of TSP for every 120 meters, so in a kind of continuous way along your tunneling. And that goes up to some 7-8 days, equivalent to your time-dependent site cost, what TSP costs for an 8 kilometer long heading. So if you express this in relatively words, so it's between below 1% and below 2% of the site costs you have there. If you now compare this with, let's say, an unforeseen incident, for example, a water ingress or a fault zone you encounter, it usually creates, if it's unforeseen, it creates downtime on your site. So at its best, it creates 3 days downtime. You see, this is exactly what TSP costs for a 1 kilometer heading here. So using TSP gives you just maximum 3 days downtime in costs. If that would take a month, you see what the costs are. If you can avoid this 30 days of site-dependent site costs created by an incident of water ingress or fracture of fault zone, having 30 days downtime, it creates much more costs on your site. There are different offerings, as you see here. So we are also caring for, let's say, the economical. So what is the most economical offering for a construction site, which is going only a short time, maybe 6 to 12 months only, where we offer also a kind of fusion rent. Fusion is something what we call when it is a fusion between us and the customer. So the customer is buying a complete system, hardware and acquisition software, and we, as an expert, do the data processing for the customer. This is what we call fusion. That can be quite efficient and economical in certain project lengths. But we can also offer here a full system hardware and software sale when it comes to longer projects, like we have at Rockfast project, for example, where they use the integral type here, everything purchased and everything done by themselves. Yeah, and that leads me to one example here from the Rockfast tunnel, where TSP is currently in operation, but it started also some years before it had this break. You know, this break, I think it was due to some political reasons, but now it's going on. Luckily, that's fine. And in the first stage, we had this kind of situation where the tunnel phase was over here, and for an access tunnel in this project, and there were let's say some suspects about an abandoned tunnel which should lie some 90 meters ahead of this phase situation here and some 70 meters above the planned tunnel roof. But nobody really knew where this abandoned tunnel was. So we did a survey, also we did a campaign here with TSP and created a velocity model. You see here a P-wave velocity model, and you actually see from this cuboid here that it turned out that a low velocity zone came here in, which is here shown in blue color. When we extract this as a surface rendered anomaly, you see here this low velocity anomaly quite clearly, and which was actually presenting this abandoned tunnel, which is, of course, a high contrast as a cavity-like feature in the rock mass. Also, from different perspectives here, you see also about the accuracy, how we could extract this from our model. Yeah, that is all. It's 1:45. I think I did it quite good in terms of time. And I'd like to thank you already now for your attention. And we can now, of course, go into Q&A session if you like.
This is Philippe.
What about Philippe?
Yes, hello, Philippe from Amberg. Quickly, put on my camera so you can see me. Hello. I'm responsible for the sales of this system in the Scandinavian country and of course in Norway. People are like, and Thomas mentioned, oh, it's expensive. Yeah, if you put that in relation to the whole tunnel project, it's definitely not expensive, considering you can mitigating your risk. We're talking pricing. I mean, you've seen these 4 different models. We have a starting price from around 25,000 Swiss francs for one investigation, which give you a certainty, nothing lies ahead of you for the next 150 meters. So there's a span from 25,000 Swiss for a single investigation. There's nothing from you. It's purely cost. We will bring the equipment, do the acquisition together with you, and do all the processing and the reporting. And of course, the last one, the full integral system, there we're talking without training from around 250,000 Swiss. So all depends on like he showed nicely, how long duration, how big the project, what's the metrics of the project, and how often you're going to use it. And in Rockfast, as you better know than me, it's like a twin bore 25 drill blast with access tunnels and shafts, etc., etc. It was worthwhile for Statens Vegvesen to acquire such a system, to have it on site, to be able to get information on what lies ahead. So we're looking at a span from service to integral from 25,000 to 250,000, just to give you a bit of a number that you're aware of what we're talking about. That's all I have to say. Now we're waiting for your questions if you have any.
Yes, Tobias.
Yes, Tobias Jokisch, geophysicist at Field. Thanks for the interesting talk. Very nice to see that the system has evolved, and I've got a couple of questions. The first one, how do you get a 3D image out of a 2D layout? This is my first question.
Yeah. Well, it's actually not a real 2D layout. We use, for example, in this case here, we use, so we are quite flexible. We use 2 shot lines, and we have different locations of our receivers. And what you see here is actually, this is the model which we create out of this. So it's a model of, when it comes to velocity of a quarter of meter to half meter increment, where we create first an initial velocity model by using the direct wave speed, which we directly measure from the shot points to our receivers at different scenarios here. And this initial velocity model is built up. So every grid point gets this point, that gets this value. And then by using the reflection information, and here, as you know, we are using 3-component sensors. So we're analyzing here at our sensors where the wave is coming from. So we have X, Y, Z information, and we do a true 3-component processing over here. So we analyze exactly the direction where the wave is coming from, and that gives us the spatial information in this. Once we can then, from the migration image, so we have a 3D migration model then using the 3D velocity, build up a 3D migration, and we can then get this 3D information from the 3D migration process. What we do then from the 3D migration, we extract the most interesting, let's say, energy areas. So like ellipsoids from the migration. And this is a self-automatic process or semi-automatic process where we extract these ellipsoids from the migration, and we're presenting reflectors, or also in other terms, we can also use the migration, but also the velocity from the 3D velocity model. That
Okay.
is the, yeah. Mm-hmm.
Then the follow-up question would be: Do you have a sort of an attribute which is the illumination that shows you which areas have been illuminated and which haven't? Because I suppose there's areas which you don't illuminate then.
Yeah, that's right. That's right. That is what we see from the migration, of course. What we actually do in the pre-processing before it comes to the 3D migration process, we look only into the ahead direction and to a certain extent to the side direction. So we are not interested in reflections coming from the back. So so from the stretch which has been already excavated. So we are focusing on let's say just the ahead area. So that gives us a kind of illumination of this interesting area ahead. And so in the migration we only consider this. And then we, as I said, the 3D information and also the direction from the XYZ component gives us so we analyze let's say the angles in a polarization analysis of the incoming wave. And this is the way how we then trace back into the model the reflection points, reflection elements.
Okay.
Yeah.
May I ask a second question? Oh,
of
that
course.
would be
Yeah.
the third one. There was one slide where you showed the type of bedrock. Is that based on some additional information about the geology in the area, or is that just simply from the physical parameters like P and S wave velocity and so on?
What do you mean with kind of bedrock?
You were showing a plot saying this is gneiss and this is fillet and so on. But the like type of rock, was that based on some a priori information based on a geological map from the surface or something like that?
Yeah.
Or is that so that's not pure
no, that's not possible. So we can.
No, exactly. Good.
That's not possible. This is, of course, as I said, it's a simplified model, and we have, of course, and we need, of course, some pre-information from the geologists on site. And this is why we say the system is in best hands on site with the on-site people. So, for example, it should work with the geologist on site. So the geologist knows, okay, right now we are here at the moment of our measurement, we know that we are in phyllite. So, and we might expect something ahead of the phase, which is a kind of transition to a rock formation, which might be gneiss, of course. And when you do this the first time, then of course you try to calibrate the velocities to this specific lithology here. But as you know, as a geophysicist, this is a kind of ambiguous information. Just from the velocity value itself, you cannot judge about the lithology.
Yeah.
So,
okay.
Yeah. But
Just wanted to get this
it's an ongoing process of, let's say, you see, the best information we have from the direct waves in this area. So here we can measure very, very precisely the velocity. And once we know what is the already excavated stretch here, we can calibrate this velocity with the lithology. And that helps us also then for all the measurements we do in the future here in this project. Mm-hmm.
Okay, thank you. The time is running. Now it's MTR Diabasen. Who are you? You have a hand up.
Hello, yeah, that's us from NGI in Oslo. My name is Tom Hansen. I just want to ask about the pre-processing after collecting the raw data. Can you describe briefly how you pre-process and what's included in the manual process? And could that, for instance, be automated in the future? Are you working, I guess, such a goal?
So yeah, it's not really visible here in this very small. I can make it a bit bigger here. For example, this is just a screenshot from our software flowchart. You see, first of all, we have a survey processing, so processing each receiver gather so a combination between receiver and shot line in a let's say separate way. We have time variant high cut, we have bandpass filters here, and we do automatic first arrival picking, of course, and we do also then an adjustment of the direct waves, because sometimes you have, which is kind of static correction, because sometimes you have, due to using wrong detonators, you have a delay on the first arrivals, and we have to adjust this. This is more or less also already done automatically. What we then do is we analyze the Q factor, so absorption over here, which we then apply later on in an inverse Q filter. So we try to bring back the energy which is being suffering by absorption, which we lost by absorption and spherical divergence. And once we have done this, we extract reflections and we separate waves. So we do the extracted reflections by a radon transformation, actually, so separating direct waves from the reflected waves by using a radon transformation, and then we separate the waves by polarization analysis. So separating in a way that we have P as V as H waves by a polarization analysis, as we have 3 component data. And then once this is done up to here, as you see, then we go into the so-called 3D processing. And so here, from that moment on, we just talk about P as V as H models. So going into the analysis of velocity, as I a bit described before, do the 3D depth migration. So it's a Kirchhoff depth migration in 3D. And once we have the migration done, we do then an event extraction, which is more or less also automated already. And extraction of the most dominant or most prominent energy elements, ending up in a reflector extraction. And then once we have reflector extracted, then we look at the locations of them and go back into the velocity model and assign a velocity value from that area to the model. So this is how we create then later on the charts. So this is very briefly how we do this.
Do you think you can fully automate that process in the future?
Yes,
because
I think
now I think it could be some subjective decisions made in the manual process. Yeah.
That's right. There could be, because for every little step in here, you see, the user can go in and change processing parameters. So in many cases, we have a kind of self-setting parameters in the processing here, which is not just a default value from experience. It's really looking at, it's analyzing the frequency content of the survey, and it's extracting out of this, for example, the wide bandpass filter limits. So it's really data dependent automation. When it comes to the 3D processing, yes, there is room for some improvements. We look at this at the moment, but also when it comes to the interpretation, which is much more important, of course. Yes, we have the right model, then how to interpret it. This is, of course, the most essential, let's say, topic for, let's say, issue for the geologist, for the civil engineer on site. So how interpret the data. And here we try to go new ways with using also KI methods, because we are really sure, and we believe in that there's a strong dependency between our parameters, of course, and geotechnical parameters and geological parameters. This is for sure, but we can use machine learning algorithms in future to extract the right information out of this. So this is what we like to focus more on. But you're right. I mean, there is always room for improvement also in the automation. Good.
I guess the
No.
person who has asked the question has left as is 1 o'clock. Yeah, but yeah.
I've got one more question. You said that the frequencies were or you look at the frequencies above 100 hertz. What about the frequencies below 100 hertz? Because resolution also comes with bandwidth, and
yeah,
is that too noisy, or what's the issue with those?
No. I mean, below 100 is of course. I mean, we are not, let's say, strictly say everything below 100 is out of question. You see here, for example, there's a frequency spectrum, an amplitude spectrum seen here. So in this case, you see this is the way how. So we analyze this spectrum and set then the high and low cut parameters out of this analysis of the spectrum. When there is something dominant below 100 hertz, then we keep it, of course.
And surface wave experiments that has stopped or is not relevant?
Well, so surface waves partly in there in the data, but when it comes to, you see, to the separation of the wave types in the radon transformation, we can get rid of them. So we are not actually interested in surface waves in this method here. So here we are just analyzing body waves.
Okay, thanks.
Very geophysical specific question. Thank you very much. Are there any from, let's say, civil engineers?
Now, there's no more hands and nothing in the chat. Please feel free, and if you want to say something in Norwegian, you're welcome to, and we'll try to translate. But first of all, I will thank you, Amberg, for very good presentations. It was very interesting, and I hope some more will contact you afterwards, and myself, I will remind you all of a small conference at the Scandic Fornebu, the 20th of April. Amberg will have a presentation there also. And if there's no more questions, or I will just say thank you. Thank you also for good questions and very good answers. So,
yeah, I also like to, I mean, I can only say likewise. So I'd like to thank you for this, giving us this opportunity here. And as you said, if there are more questions also later on, please let me know. You can drop me an email under tdickmann@amberg.ch, or also contact Philippe at pmette@amberg.ch, or you can contact Joel Biedermann in Norwegian. Philippe will be in Norway in April, I think, right, Philippe?
Yes, I'll be joining this BA-Nettverket live session April 20th. I'll be there presenting Amberg Tunnel, the survey part. That's the plan, exactly.
Yeah,
so
right.
We'll have the opportunity to meet.
So if it comes, yeah, if you like to have a personal meeting as well, face to face, that is sometimes, of course, more convenient to talk to each other. So that's possible in April, but also I'm keen to visit you when it comes to a real project or whatever it is. That is our philosophy at Amberg, that we do a very, very good, that we like to have a very good relationship to our customers before and after the sale. And give a very good support, because I'm a geophysicist and I like to work. I like people to work with our products, and I like that they achieve benefits out of this. And what I also like is that I get a good feedback from our customers in order to improve ourselves. Yeah. So so any kind of question is very welcome. Thank you very much.
okay, that's all. Or do you, Joel?
No, thank you very much for Thomas and Philippe to be presenting this system here in Norway. I think there is a future for it. We see it on the Rockfast project, but we think there might be also an opportunity on the new water tunnel with TBM in Oslo, for example, that could be highly relevant. So yeah, just contact us if you have other projects where you think it could be useful. Thank you very much.
Okay, thank you.
Thank you, Inger.
Thank you all. Have a good
Thanks a
afternoon.
lot.
Bye-bye.
Bye.
Bye.
Ha det bra.
Ha det bra.